Good morning, everybody. This is Nicholas Zabaras, and we continue the lectures today on statistical computing and machine learning. So the lecture today will be the first in a sequence of lectures on sequential Monte Carlo. And in particular today, we will introduce the state space model that we will use as the driving example to introduce sequential Monte Carlo. And also it will be the driving example to allow us to introduce dynamic problems, in particularly nonlinear, non-Gaussian dynamic models, and a review as to what the target distributions and what the challenges are with this type of methods. So let's see some of the topics that we will cover today. So the lecture today contains, for those who want to visit the slides, a significant number of online resources on sequential Monte Carlo. And so the next few slides provide a list of online resources. So today we will discuss the state space model. I am going to give you the general notation that we will use in the follow-up lectures, but also a number of examples, each of them with its own challenges. And we will use the state space model to discuss Bayesian inference for dynamic settings. So we will see what the target distributions are and what are the challenges in applying Monte Carlo methods for these dynamic setting problems. And eventually I'm going to bring back the ideas of Monte Carlo sampling that we have seen earlier. In particularly, I am going to apply standard Monte Carlo and importance sampling to the state space model. And then in the follow-up lecture, we will be ready to start addressing sequential Monte Carlo problems. So the objectives for the lecture today will be to review the state space model, to address the key ingredients of Bayesian inference for dynamic settings in the context of these state space models, and of course to discuss the application of standard Monte Carlo and also important sampling for the state space models. So again, the follow-up slides have lots of online resources, and none of them are really up to date, but lots of these references are fundamental and are being used throughout the lectures today and the next sequence of lectures as well. So if you search, you will be able to find more up-to-date lectures, but this will be sufficient for the discussions we're going to have in today and in the next few lectures. All right, so let me go directly and start discussing about sequential Monte Carlo. I want you to think of sequential Monte Carlo as an alternative sampling method to Markov chain Monte Carlo, and both of them are made with the objective of being able to sample from high-dimensional distributions. Now today we will discuss sequential Monte Carlo in the context of dynamic problems, and that's where SMC methods are mostly known, but please keep in mind that you can apply sequential Monte Carlo to sample from any high-dimensional distribution without any dynamics in your model. All right, so the method is asymptotically bias-free, and what I mean asymptotically bias-free, if you think of representing this with Monte Carlo samples, as the number of samples goes to infinity, asymptotically you do get a bias-free approximation. So that's nice. However, the method sequential Monte Carlo turns out to be computationally a very expensive method, especially in high dimensions. Now, if you want a cheap method, basically using variational methods such as expectation propagation are more relevant methods. They're very cheap, but you have to keep in mind that variational methods have the deficiency that you're doing approximations to high-dimensional distributions. So, for example, you may factorize a high-dimensional distribution as the product of univariate Gaussian distributions. So that's a very drastic approximation that may not be useful for a particular problem. So sequential Monte Carlo is expensive, but obviously has lots of merits, and that's why it is a significant subject of research for the last 20 to 30 years or so. Okay, the applications, of course, of sequential Monte Carlo are all over the place. And as I mentioned, dynamic settings is the key area where you will see sequential Monte Carlo, but they go much beyond that. So you will see applications in engineering, in chemistry, in biology, in robotics, such as terrain navigation, trajectory planning, in purely computational mathematical tasks such as solving equations, computing eigenvalues. Those will be applications similar to what we have seen with MCMC methods. You can use this in chemistry to simulate polymer chains, to compute free energies. Of course, since the setting of dynamic models is very relevant, you will see this in econometrics. If you want to follow, stock predictions, the stock prices, that's a very relevant task. Also in speech enhancement, and I'm going to give you an example today in the early part of the lecture, in epidemiology, etc., etc. Okay, so now again, the lecture today and the follow-up lectures, we will use the state space model as our driving example, and if we have time, maybe we can have another lecture where you will see applications of sequential Monte Carlo outside the state space model. So, by the way, in engineering, sequential Monte Carlo methods come with other names that may be sometimes misleading. So a common name is particle filtering or smoothing methods. Both of these names are relevant, but however, they are more focused in what they exactly imply. Sequential Monte Carlo methods are much more general, beyond filtering and smoothing, as we will see even in the lecture today. All right, so I would prefer to call these methods sequential Monte Carlo rather than alternative names that you may see in the literature, especially the engineering literature. So let me introduce the notation for the state space model. So at first I'm going to start with a Markov chain that you see in the bottom. And the key assumption that I'm going to make for the Markov chain is that I have an initial density mu from where I can sample x1. And then I have a transition kernel. I have a rule that tells me how to go from the state at time n minus 1 to the state n. And this transition density, I call it here f. And I'm going to refer to f as my dynamic model, right? It's the model that tells me how to transition from a state at one time to the state at the next time step. And now I emphasize this Markovian model. And Markovian model, for those who forgot, implies here that the xn depends only on the previous state xn minus 1, okay? So the dependencies are only from the previous state, and this probabilistic graphical model that you see on the bottom represents basically, in a graphical sense, these dependencies. So for this Markovian model, I can write the prior distribution of the states with this equation. So let me introduce the notation here. So when you see bold x with subscripts 1 to n, this implies x1, x2, xn. So it's the joint distribution of all the states in the chain up to time n. All right. So this is p of x subscript 1 to n. And this, of course, is my probability of sampling x1, and then the probability of transitioning from x1 to x2, and the probability transitioning from x2 to x3, all the way up to the state n. So this is what I call the prior distribution, because in a little while I am modify this Markov model to introduce measurements, and at that occasion we will see the likelihood, and then of course we can talk about the posterior of the states x subscript 1 to n. All right, so let's see a few trivial examples. Let's say that you want to track an object, let's say a missile, or and here I'm referring to an object in the plane xy. So I'm defining the state of the missile based on its x and y locations and velocity components. So xk1 is the x, is the x component of the missile. Vk1 is the x component of the velocity of the missile, and similarly for x2 and v2. And k, it's the indicator that refers to time instance. So at time k, this is the x components of the location and velocity, and these are the y components of the location and the velocity. So what I can do is I can write a constant velocity model that looks like that: xk equal a times xk minus 1 plus some Gaussian model, right? And the matrix A here that I have consists of these blocks, A subscript CV. CV implies constant velocity model, and each of these matrix A CV is 1t and 0 to 1. In some sense, if you look at this equation, the model that you write for the location looks like an integration scheme using the velocities to predict the location at the next time instance. But right now, really, we don't want to go to those details. Effectively, we are just describing the evolution of xk, the transition model from xk minus 1 to xk with this nice linear equation where this matrix A is constant, is given, and I have a Gaussian noise here defined by this covariance metric sigma that you see on the bottom. Okay, so this is a typical tracking example, and of course you can come up with your own tracking model both in 2 dimensions and in 3 dimensions. So the transition probability for this model is nothing else but it's a Gaussian, as you can see, since my nose here is a Gaussian. So transitioning from xk minus 1 to xk, the probability of xk has a mean a xk minus 1 that you see here, and of course has a covariance sigma defined by this noise model for w. Let's look at a model related to speech enhancement. So let us assume that we have, speech signals that I denote here at time k. I denote the speech signal as sk. So what we're going to do is to define sk. We're going to introduce what is called an autoregressive process. So sk is going to be a linear combination of the previous d values of the speech signals. This is what I have here. All right, so alpha I are coefficients, and I say that the speech signal at time k, it's a linear combination of the speech signals at the previous d time steps. So this is k minus 1, k minus 2, k minus d, and then of course I have a Gaussian noise. Now you may say you don't recognize this as a Markov model because now you see somehow a dependence of sk from the previous d signals. However, you can rewrite this as follows. You can introduce uk as a new state that consists of the signals at time k, k minus 1, k minus d, and then you can actually summarize this equation that you see there as uk equal to a times uk minus 1 plus b times vk, where you can see effectively when you take a and you multiply with uk minus 1, the first element that will provide you the value for sk will be the linear combinations of the d previous values, and then the remaining things don't introduce any extra information. So for example, from here, if you look carefully at the equation, it doesn't tell you anything but that sk minus 1 is equal to sk minus 1, sk minus 2 equal to sk minus 2, etc. But this matrix notation allows me to write these speech signals as a Markovian model, the way that we saw in the very first slide in the lecture today. So the transition density for this model going from UK minus 1 to UK is again a Gaussian, and let's pay some attention first what we have here. You notice because d minus 1 of these components, okay, do not change, all right? You remember I said here that sk minus 1 on the left-hand side here is equal to sk minus 1 on the right-hand side. So I denote all of this with a delta function that tells me that the values of uk from 2 to d, they're the same as the values of uk minus 1 from 1 to d minus 1. Okay? And the first value of uk, so the first component of uk, and I denote this uk parenthesis 1, is a Gaussian that has this mean, which easily you can see it's the product of these coefficients times the values of the signal uk minus 1, all right? So this is, if you take the product of a uk minus 1 and you take the first component of that vector, this is what you have here. And then, of course, you have some Gaussian noise for your model, and that's your transition density. Okay? So the Markovian model, as limited as it looks like, it can be used to actually write down in a very concise form this autoregressive model that is very common in not just in speech enhancement, but in econometrics and many other subject areas where you are interested in dynamic modeling. Now, for this speech enhancement problem, you can actually go one step further and you can say, well, those coefficients alpha that I had before, you remember the speech signal at time k was a linear combination of the previous d signals with alphas being these coefficients defining that linear relation. So now what you can say is, maybe I can even make those coefficients to actually evolve with time with their own Markovian model, okay? So what I'm going to do is I'm going to define a vector of these coefficients, so that every time I'm going to take all of these d coefficients and define a vector alpha k, and then I'm going to introduce a Markovian model for alpha k, so that alpha k is alpha k minus 1 plus some Gaussian noise. Now, if you do all of this, I can go directly to my overall transition density for my speech enhancement model, and let's see what we have here. So this is a term identical to what we had before, right? So the components of uk from 2 to d are the same as the components of uk minus 1 from 1 to d minus 1. The first component of uk is a Gaussian model with this as a mean and some noise that you see here. And then I have times a Gaussian that defines the transition of the coefficients alpha from alpha k minus 1 to alpha k, and that comes with its own noise defined by sigma alpha square. Okay? So again, that's a nice indication that you can make this rather complicated model, this AR model, where even the coefficients change with time. You can make this to fit in the Markovian model that we show in our very first early slide of the lecture today. All right, so let me move to an example in econometrics. If you look, for example, on how a stock price changes, so let's call the stock price to be ST, and we're going to write down a model for the log of ST, and I call the log of ST here XT. So d of XT is written as mu times dt plus dwt plus dzt, where zt is a jump process and wt is a Brownian motion. So for those who are not familiar, I don't want to spend much time, but a jump process is in essence a stochastic process that has discrete movements that we call jump. That's why it's called a jump process, and also these discrete jumps come with random arrival times. And the Brownian motion is mainly known for the random motion of particles suspended, let's say, in a fluid or in the air. And effectively what the Brownian motion corresponds is to random fluctuations in a particle's position inside the medium, followed by some sudden relocations to a new location, and again random fluctuations in that location, and then jumping to another location, etc., etc. Right? So the stock prices obviously can have these random fluctuations, but also they can have significant jumps. So you will need to have both a jump process and a Brownian motion to describe the dynamics of stocks. And if you want to write this in a discrete setting, you can integrate the equation on the top and write it the way that is indicated here. Again, you can read, there are dedicated textbooks on this subject and courses, of course. And this model, of course, is not limited to the price of stocks or econometrics in general. The same type of ideas can be used in biochemical networks, in population dynamics, disease modeling, and many other related subject areas. Okay, now we are ready to start extending the Markovian model, where we only had the states x1, x2, xn evolving. Right now we're going to extend it and introduce some observations at each time, and I call these observations y1, y2, yn. Okay, so what you see on the bottom is a probabilistic graphical model that defines the dependencies. And again, I don't want to elaborate too much because that is another subject area. But let me just say, we already have seen that x2 depends on x1, so you can guess that the direction of the arrow defines these dependencies. And similarly here, you can see this arrow pointing upwards from x1 to y1. It implies that y1 depends only on x1. Similarly, y2 depends only on x2, etc., etc. Okay? So this model is obviously an extension of the Markovian model that we introduced before, but now the whole focus is changing because we're going to make the states x1, x2, xn to be unknown states. We're going to have these observations y1, y2, yn, and then the objective, of course, will be using the values of y1, y2, yn to produce a posterior distribution of x1, x2, xn, and we will see the details momentarily. Okay? So obviously this is a dynamic model, right? And this can include hundreds, thousands potentially of different applications. So this is a very powerful model that you need to be familiar with. All right. So what we need to do is we need to have basically the same type of distributions that we discussed for the Markovian model. So we need to have a probability density mu to sample our initial state x1. We need to have a dynamic model that tells us how we transition from time n minus 1 to time n. So this is the evolution of the states. And remember the notation, we use f to indicate that. And now we're going to have an observation model. An observation model will tell us at each time what is the probability of the observation yn given xn, and I will indicate this observation model with this density g. So again, f will be used for the dynamics, g is going to be used for the observations. Now, as I indicated before with the discussion about the probabilistic dependencies implied by the graphical model, let me just say the following. I am going to take that the observations yn are independent of each other given the Markov states xn. So that will allow me to write the likelihood of y1, y2, yn given the states x1 as xn as the product of g of yi given xi from I equal 1 to n. So this is a very important assumption. and the probabilistic graphical model actually indicates this assumption. All right, so we're going to assume that given xn, that the observations yn are independent. So again, these two equations on the top will define the prior model for the states. This defines the likelihood, and of course from the two we will be able to come up with a posterior model for the states that we will see in a few minutes from now. All right, so the objective, at least we can say, that will be to recover xn given the observations yn. So you can think, actually, in the most trivial case, think of yn being noisy observations of the states. So if somebody gives you noisy observations of the state, you will be required to go and recover the actual values of the states xn. But we're not limited to that, right? We have this generic observation model that, as we will see, can be anything, and depending on applications, you can assign different meaning to what this density G is all about. So let me write down the simplest possible state space model, or hidden Markov model, equivalently from what we saw in the previous slide, and that's this linear Gaussian state space model. It goes with the acronym that I will use throughout the lectures, LG-SSM, so linear Gaussian state space model. And first, we call it a linear model because all these matrices A, B, C, D are constant matrices. Now, you can immediately extrapolate from here that this defines the dynamical model, this defines the observational model, but you notice I have an extra variable u here just to make things a little bit more general. So you can think of it as a known signal. So for example, if this is a mechanical dynamical problem, you can think of un being some external forcing maybe that changes with time. But right now un is considered to be a known explanatory signal. X are the unknown states and y are the observations. And of course, it says here linear Gaussian model. That implies immediately that these variables v and e are Gaussian random variables. So here is the supplementary equations to define this model. The initial state is some Gaussian model, and the noise variables v and e are also sampled from some Gaussian model. Now, the good news with this linear state space model are that there is an exact solution, right? And that exact solution goes with the name of Kalman filtering. I will not say much about Kalman filtering. I will give you actually the recursive equations that go with Kalman filtering later in the lectures, and maybe I will even provide some comparisons throughout these discussions of Monte Carlo methods with the Kalman filtering analytical solutions. But right now, keep in mind that this linear Gaussian state space model is the easiest. We can solve it exactly, but our focus will be on very general non-linear dynamical models that maybe don't fit in this Gaussian setting. All right, so here's another problem that's called stochastic volatility problem. And you can see the dynamical model, the transition model is, if I take the noise to be Gaussian, is a Gaussian model, right? But now you can see that the observation model is a highly nonlinear model because of this dependence of y on x is you have this exponential of xn over 2. So again, the dynamical model, it's a simple linear Gaussian model with this mean and this variance, and the observation model is a much more complicated, okay, because of this dependence on the exponential of the unknown states. So this stochastic volatility problem will be actually a fantastic example to test various sequential Monte Carlo algorithms that we're going to see in the next few lectures in this course. So in the context of tracking, here is a standard problem that is called bearings-only tracking. Let me put up all the equations. So what we have is we have an observation y. All right, we have an observation y. You can think, if you think a missile, let's say, on the plane, and these are the y and the x coordinates. This looks very much like the angle of where the missile is, right? So y is the angle plus some Gaussian noise, and obviously this angle is this inverse tangent of x2 divided by x1. So that's a highly nonlinear function. So the observation model here is non-Gaussian, all right? And this will introduce complications that we will have to address when we discuss about sequential Monte Carlo methods. Now, in passing, let me just say that even though this research on sequential Monte Carlo methods has been out for quite some time, for almost 30 years in research, there has been a lot of recent activity on sequential Monte Carlo, especially with the discovery now of this new framework for doing probabilistic programming. Okay, so what is probabilistic programming? So probabilistic programming uses a new programming language that is called probabilistic programming language that somehow encodes a probabilistic model to a probabilistic program. Okay, and what is new about it? What is new about it is that the memory of this program, when you run it, it's actually a stochastic process, and the way that you model this dynamic stochastic process is using sequential Monte Carlo. Now, why there has been so much interest in probabilistic programming? Because probabilistic programming, these probabilistic language models effectively make programming very efficiently. They provide a library of distributions that you can evaluate on the fly. They provide futures for probabilistic models, and of course futures for probabilistic inference. And what is important, they allow for separation of the probabilistic model from the inference that is being used, effectively allowing for automation of the inference process. Okay, so I consider this an enormously upcoming area, and let me just say again, sequential Monte Carlo is used extensively in this type of models, so you may want to visit this short but very insightful article of Zubin Garamani in Nature, or the first reference that provides some of the fundamentals of probabilistic programming and the relation with sequential Monte Carlo methods. So effectively think that sequential Monte Carlo methods can be implemented very nicely with a lot of flexibility using this probabilistic programming type of approaches. All right, so let's go back to the our state space model, having both these unknown states x and having these observations y. And so let me define what our target distribution is going to be from now on for the rest basically of the lecture today and the follow-up lectures. So the target distribution is going to be the posterior of p of x from 1 to n, given the observations y from 1 to n. Okay, so you can observe first that this sequence of posterior distributions becomes higher dimensional rapidly. So at time 1, your posterior is p of x1 given y1, time 2 is p of x1 2 given y1 2, and then maybe at n equal a million is p of x1 to a million given y from 1 to a million. So you can appreciate the complexity of the problem increases, and our focus will be, can we come up with techniques that somehow keep the computational cost under control, so the cost of going from one time step to another in computing this posterior distribution doesn't actually increase exponentially. Can we do this? And we will see how sequential Monte Carlo methods will allow us to do that. For now, I am writing down the prior model that we have seen for the Markovian model, and then this is our likelihood model using the dependence of y's given the x's, right? And if you multiply those together, you will effectively get the normalized posterior, and this is what is going to be used in our analysis. So obviously this is time varying, it's a dynamic model, and this is what the setting that we're going to use in the lecture today and the follow-up lectures. All right, so the target for the discussion today will be this posterior distribution, but in the literature, and maybe depending on your interest in different applications, maybe you're really not interested in the whole posterior of x from 1 to n given all the observations. Maybe the only thing you're interested in is what is called the filtering distribution that gives you the posterior of xn given all the observations from 1 to n. So this is what is called the filtering distribution. You notice there is no bold, so this is, I'm assuming here, this is a scalar variable. Of course, at each time, x can also be a vector, but just to distinguish from this x, I denote this as an unbold x. So that's the filtering distribution. You can also think of the predictive distribution. So if you have observations up to time n, this is the probability for the state at n plus 1 being x, n plus 1. That's the predictive distribution given the observations up to time n. And of course, if, let's say, you're going to run this dynamical model up to a total time of capital T, then maybe of interest is to compute the joint smoothing distribution. So to compute the joint distribution of all the x's given all the y's, or maybe to compute some marginal smoothing distributions. So if you go back at n less or equal to capital T and you say, what is the probability of xn given all of my observations, not just up to time n, but all of my observations from time 1 to t, that's the marginal smoothing distribution that is, of course, significant for offline type of calculations. And again, I emphasize that for linear Gaussian state space models, all of these distributions can be computed analytically using the Kalman filter, but our focus will be to come up with Monte Carlo approximations that are applicable to general nonlinear, non-Gaussian models. All right, so we're ready to start talking about Bayesian inference in the state space model. Let me just put up all the equations, all right? So this is our prior, this is our likelihood, and this is the posterior. Okay, so I need to introduce here carefully some of the notation to be sure that things are clear. So we're interested in the posterior of all the x's given all the y's at time n. So I am writing this as the joint distribution divided by the likelihood p of y from 1 to n. So the anormalized posterior is this joint distribution that you see here, right? This is the anormalized posterior. So you will see often in the lectures that I'm going to be using this anormalized posterior because you remember always we want to use Monte Carlo methods that don't require that you know the normalization factor of your target distribution. So these joint distributions of the x and y is the prior model that we have seen here times the likelihood, and I'm writing all of this now explicitly, and you need to be sort of very aware with this expression because this is the type of model that we're going to use. So this is the probability of sampling x1. This gives you the probabilities for transitioning from x1 to x2, from x2 to x3, etc. And these are your observation models, the probability of observing y1 given x1, y2 given x2, etc. And In the literature, you may find some textbooks give you this product as one product with a little bit different indices, but just to be consistent, this is what I am going to use in the lecture today, as well as in the follow-up lectures. All right, so let me introduce a notation for the target posterior distribution. So I'm going to call the target posterior distribution pi n of x1n. Obviously, the subscript n is going to remind me that this is the posterior at time n. The argument here is going to remind me that this is a distribution in the variables x1, x2, xn, and I don't show you explicitly the observations, right? But remember, we're looking for a posterior distribution given the y's. We're trying to compute the posterior of all the x's. So the anormalized part of the target posterior distribution, so that's the joint distribution of x and y, I am going to denote it with the letter gamma n of x1 to n. So this is what I am going to use to simplify the notation from now on. So gamma n is going to be the anormalized posterior. And the anormalized posterior, remember, in our problem is nothing else but the joint distribution of x from 1 to n and y from 1 to n. And one more piece of notation. The normalization factor here, I'm going to denote this as Zn, and the normalization factor is nothing else but the probability of the observations y from 1 to n. Okay? Now, again, if the model is linear Gaussian, I can compute everything I need in a closed form solution. Actually, I can generalize here a little bit, and we will see the details later on. So if the dynamic and the observation models are linear Gaussian, then we can use Kalman filtering type of equations. But also if the state is finite, all right? So if these states xn take values in finite state space, and we have the so-called finite state space hidden Markov model, then we can compute the marginal and the joint posterior of the states in a closed form. Okay, but again, we're interested for the nonlinear, non-Gaussian case, so we will try to be as general as possible. Now, the objective is to compute the posterior of all the states given all the observations. All right, but maybe somebody is interested to compute the map estimate of this posterior. All right, so that can be a problem, or maybe your interest is to compute the marginal posterior of xk. So that's basically the posterior with all other variables but xk integrated out. Or maybe you're interested in the posterior mean, so you're interested to perform the integration that you see in the equation at the bottom, on the bottom of this slide. Now, one way or another, if we can compute the target joint posterior of all the x's given all the y's, then all of these tasks would be answered immediately as a byproduct of our Monte Carlo approximations, as we will see. So let me do one example to show you where someone may be interested in computing the normalization factor rather than the posterior of the x's given the y's. Okay, so I'm going to give you a very practical example where the focus is on computing the normalization factor, and that way later on when I give you approximations of the posterior, I'm going to make an effort to also give you the corresponding approximations for the marginal likelihood, right, for that z factor in the normalization of the posterior. So let me introduce the following example. Let me interpret G. You remember G was our observation model at each time. So let me interpret G as follows. I'm going to consider that I have a particle that moves from one state to another, and I'm going to define the probability that this particle is killed at time n, as 1 minus g at xn. So if the particle is at time n in the state xn, the probability for this particle to be killed, all right, is 1 minus g of xn. So obviously g of xn is the probability that this particle will survive at time n. So let me elaborate a little bit. Okay, so let's say that we want let's define capital T to be the time that the particle is being killed, and we want to compute what is the probability that that time is greater than n. All right, so again, capital T is the probability that the particle will be killed, and we want to find what's the probability that capital T is greater than n. Okay, obviously in computing this, right, if a particle is going to survive up to time n, what that implies is that the particle has to survive at time 1, has to survive at time 2, at time 3, all the way up to time n, and that calculation will actually give us the probability of capital T being greater than n. So let me go rapidly through these equations and say that if you want the particle to survive at time 1, this is the underlying probability of survival at time 1. Why is that? Because for the particle to survive at time 1, it has to be generated at some state x1, and then it has to survive at that state, and you remember the probability of survival is g of x1. And because x1 is a random state, this probability of survival at time 1 has to be this integral on all possible values of x1. How about at time 2? I can do exactly the same thing, right? For a particle to survive at time 2, first it has to be generated at time 1, it has to survive at time 1, then it has to transition to state 2, and then it has to survive at the state 2. So the integral of what you see on the bottom in the states x1 and x2 is going to give you the probability of this particle surviving up to time 2. Now you can immediately see that really what I have here is I can see generation of my dynamic model, that's the evolution of states, and see here the product of my observations, the probability of the observation, so that's my likelihood model. So literally what you see the marginal likelihood coming up in defining this probability that the particle it survives up to a given time. So if I can go directly to the final equation, this is the probability for the particle to survive at time tn, right, is nothing else but the normalization factor. That's the normalization factor that comes in the Bayes rule, right, when we wrote the posterior of the states x from 1 to n given all the observations. So the normalization factor turns out to be the essential element that we need to compute the probability that the particle will survive up to time n. So obviously this normalization factor has much more significance than this trivial example of survival of the particle. And for those who are studying statistical mechanics, you can start thinking on how this normalization factor is related with free energies and how free energies are related with most statistical and thermodynamic properties of interest in practice. Okay. So again, that's the conclusion for our example, right? The normalization factor is extremely important here, and I remind you the notation that I wrote the target posterior. So remember, this is my target posterior. I wrote it as the anormalized posterior. So that's the join of x and y, and I denote here as gamma n, and Zn is the normalization factor. So remember both the pi n, the gamma n, and the Zn notation, because we will see those coming up practically in every slide as we move forward. All right. So we discussed already that for linear Gaussian state space models, Kalman filtering basically will give us the exact solution. Actually, we will see in passing in follow-up lectures, because we do have analytical solutions for linear Gaussian models. One of the approaches to handle non-linear non-Gaussian models is somehow to make them linear Gaussian models, and ideas of using approximations to do that are going to come to play a role. Okay, one way or another, I want you to remember that for these non-linear dynamical, non-Gaussian dynamical models, we will employ these so-called sequential Monte Carlo methods, and these sequential Monte Carlo methods will be asymptotically consistent, and asymptotically consistent here implies that when I compute with these Monte Carlo approximations the expectation of some function phi of the state, that will converge to the true expectation asymptotically as the number of Monte Carlo samples increases. Okay? So of course we will need to establish a lot of these details as we move forward. Now again, if the model is non-Gaussian, you may see specialized books that define Gaussian approximations to non-Gaussian dynamic models. So things such as the extended Kalman filter, the unscented Kalman filter. You can see methods that go with the name Gaussian sum approximations. If I recall, the key idea here is again to take any sort of complicated PDF and write it as a mixture of Gaussian PDFs. So approximate basically whatever non-Gaussian model you have as a mixture of Gaussian models. All right, so that's the Gaussian sum approximation. Similarly to variation methods, you can apply what's called projection filters. All right. And actually what you can do is you can also discretize the state space model and use either analytical expressions, because I mentioned on finite state space model, all the integrals become summations and you can get analytical solutions. But keep in mind, these methods don't really work in high dimensions, and not only that, they are not very reliable, and it's not going to be easy to diagnose if they are failing and why. Okay, so we need numerical approximations, and I had mentioned in long time ago, if many things fail, the only method left to actually work with is Monte Carlo. So what we need to do is we need to explore how Monte Carlo can be applied for this dynamic setting in a way that does not increase the cost exponentially with time. All right, this will be our task for the follow-up for today and some of the follow-up lectures in Sequential Monte Carlo. Okay, so I'm going to go back and review for those who forgot about those things, the key ingredients of Monte Carlo methods, and then I'm going to review important sampling, and then in the follow-up lecture we will proceed with sequential important sampling. But today I'm going to remind you the Monte Carlo fundamentals, the fundamentals of important sampling, and then I'm going to apply those to a dynamical setting, so extending the notation to the state space model. All right, and our target distribution, remember, is that unnormalized posterior gamma n. So I'm going to try to write Monte Carlo methods with the notation appropriate for our target distribution. All right, so Monte Carlo methods, I'm going to go very fast so we don't spend time repeating the same things. Remember, the idea is we have some distribution pi, and we want to compute expectations of different functions f of x under the distribution pi of x. Okay, we assume that pi is known up to some normalization constant, and again here, to be consistent with the notation in these lectures, I write the normalized part of pi as gamma. Z again is the normalization factor, and we're assuming, of course, that z is difficult to compute, so we will hope that we don't need to know what z is. As a matter of fact, we will hope that we will be able to compute z with Monte Carlo approximations. So we introduced the empirical measure for pi, right, for standard Monte Carlo. So we sample x of I, and this is the empirical measure that I denote here as pi hat of x. And using this empirical measure, if you substitute instead of pi, use pi hat, then the Monte Carlo approximation of the expectation of f under pi is nothing else but this sample mean that you see here, where again the samples are coming from the target distribution pi. Now, if x here is a high dimensional vector and you are only interested in marginal distributions, you can actually compute this very easily as post-processing. So if you want to integrate all the variables out except the variable p, the marginal of xp would be nothing else but this empirical measure that involves only these delta functions on the components xp. I'm also indicating here the central limit theorem written down for the standard Monte Carlo methods, and I remind you that the method is unbiased. So the expectation of the Monte Carlo approximation is the true expectation of f under pi, and I also remind you that the variance is 1 over n, the variance of f under pi. Okay, so so this would be useful, rules that we will try to use as we move forward. So remember again, the Monte Carlo estimate is unbiased, and the variance is given as 1 over n, the variance of f, and we have the central limit theorem to summarize both of these results together with the equation that you see here. So obviously when you sample from pi of x, the idea here is the samples will come from the regions where you have high probability mass, but as we know by now, it is very difficult to sample from high dimensional distributions. Okay, so sampling directly from a high dimensional distribution is not going to be easy, and that's why we introduced this concept of importance sampling, where the idea was, how about if instead of sampling from pi of x, we sample from some proposal distribution q of x. All right, so that's how we came with importance sampling. So again, the idea is this distribution here is very difficult to sample directly. We will instead sample from q of x, and the only assumption that we make for q of x to start with is that the support of q of x includes the support of the original distribution pi of x. So in regions where pi of x is positive, q of x is positive as well, right? And this is the fundamental equation that we use in importance sampling, and it looks very cryptic for those who forgot about it, but if you look carefully, this equation is rather trivial. So let me discuss it a little bit. I have introduced here the unnormalized weights, that is my gamma of x, that's my target unnormalized distribution, gamma of x, divided by the proposal distribution q of x. So this is what I call little w. These are my unnormalized weights. So you can immediately see if you plug in w as gamma over q, right? Q and q will cancel, and actually what you get here is you get gamma divided by the normalization factor. And note the normalization factor, if you plug in w to be gamma over q, is really the integral of gamma of x dx. All right? But here, this equation is very useful because if you can come up with a Monte Carlo approximation of q, then immediately you have an empirical measure for pi of x, starting with the empirical measure for q of x. And that's exactly what we're going to do, right? So if you start with an empirical measure for q of x, so if you sample n times from q of x, and q hat is the empirical distribution q hat, then what we can do is we can plug in that in here and get the empirical measure for pi of x, and that's what you see on this slide. There is a lot on this slide, and we have seen a lot of these details when we discuss importance sampling. So let me just summarize. What I'm going to do is, instead of Q in the previous equation, I'm going to use the empirical measure of Q, and this would lead to an empirical measure for pi. And then what I'm going to have is, I am going to have in the numerator 1 over n summation over I of the unnormalized weights evaluated at each of the samples xi times these delta functions. And then in the denominator, what you have is, if you put the a Monte Carlo approximation for Q, if you put the empirical measure for Q, really what you have is a standard Monte Carlo approximation, for this integral of, for this expectation of W of x. So a standard Monte Carlo approximation would be nothing else but 1 over n, the summation from I equal 1 to n of W of xi. So effectively what you get here is you get the ratio of two Monte Carlo approximations, and I can put those together by taking this little w and divide it by this summation to define normalized weights capital W of I. And that immediately gives me my final form for the empirical measure of pi of x under this important sampling methodology. Okay? So again, little w are the unnormalized weights, all right? They're the ratio of gamma over q, and capital W are basically the little w's divided by the summation of all the w's. So remember, unnormalized weights, normalized weights. Now, for those who have hard time to actually see how this equation is being derived, so plugging in the empirical measure for Q and then getting W evaluated at each of your samples xi, what you can do is simply take take the empirical measure from Q, so sample from Q, and compute the expectation of any function phi of x using samples again from Q. And when you do that, you will see that the final result corresponds to an empirical measure for the original target distribution pi that is given by what you see here with this blue equation. Okay? So from now on, I am going to assume that the important sampling distribution, the empirical measure for important sampling for pi, is the summation of this capital W weights. And I remind you, capital W are the normalized weights. And these are delta functions at the samples that are samples extracted from the importance distribution Q of x, all right? The importance distribution Q of x. Now, the way that I actually have done the evaluation here in the denominator, you can see that immediately transfers to the idea of computing an estimate for the normalization of my target distribution. Remember, my target distribution, the normalized target distribution is gamma of x, all right? So really what I need is I need to compute an approximation of gamma of x dx. So if you multiply and divide by q, so this is the normalized little w weights, and now what you can do is you can plug in the empirical measure for q, and you can do standard Monte Carlo, and the Monte Carlo approximation for the normalization factor z is nothing else but 1 over n summation of little w evaluated at the samples xi, where xi are again samples that are drawn from the important sampling distribution Q of x. Okay, so we're able with important sampling to compute both the empirical measure for pi, and we're ready to, we can compute immediately the normalization factor, an approximation of the normalization factor z. And the only thing, again, I will remind you, in the difference with standard Monte Carlo, since these sample sets are not coming from the distribution pi, they're coming from the distribution q, that discrepancy has to be accounted for, and the way that is being accounted for is through these normalized weights that here I denote as capital W. Again, little w are normalized weights, capital W are the normalized weights. Okay, and again, as I mentioned before, if you want to test it, take the expectation of f of x under this target, under this empirical measure pi hat that we computed before, and it turns out that is nothing else but f of xi times wi. Okay, again, we are accounting for this discrepancy that I mentioned before with these weights wi. How about a central limit theorem for importance sampling? We can come up with that. And you remember we have used, when we discussed about importance sampling, we used the delta method to show you that importance sampling estimates are biased. So if you take the expectation of this approximation, it turns out that it's not equal to the true expectation of x. So this is the bias term, and you can see here the bias is 1 over n times this. So bias square is being reduced with n as 1 over n square, and the variance is 1 over n times this expectation. It may be useful to actually remember these expressions. Notice here you have the expectation of the normalized weights w, so this is big W, times f minus the expectation of f, and here for the variance you have w f times minus the expectation of f squared. Okay, and again, remember here these are the normalized weights, capital W. Okay, capital W. And of course, you can put those two together, and you can write, a central limit theorem for importance sampling as well. So if you try to come up with statistics of the approximation for the normalization factor of our target distribution, so if you want statistics of z hat, all right, since we actually did nothing else but use standard Monte Carlo here, the expectation of z hat is equal to the true value of z, and the variance is nothing else but 1 over n times the variance of the unnormalized weights w that you see here. So these are standard, again, Monte Carlo approximations. Again, you have to be very careful in the notation here, right? So since I do standard Monte Carlo estimate of this expectation, this is my little w, and I take expectation with q. Obviously, the variance will be the expectation of w minus the true value z square, right? Under the distribution q. Now, what do you choose? What do you choose as q? Remember that the variance of the weights, if I can go back actually on this slide here, right? Effectively, this gamma over q are my weights, right? So the variance of the weights is what you see here. This is the variance of the unnormalized weights. So this first term is nothing else but the expectation under q of gamma square over q square. That is nothing else but really an integral of gamma square over q. So really, we would like to have this integral to be finite, right? Now, this is a very difficult thing to remember and also to evaluate. So computing q so that this integral gamma square over q is finite. So in practice, people are very happy if you find the distribution q so that the unnormalized weights are bounded, and that reminds us very much what we did with importance sampling, which means that you need to select q, that q basically, the support of q includes the support of pi, and more importantly that q has heavier tails than the target distribution pi. Okay. So let's now take this notation that we have seen for Monte Carlo and importance sampling and apply it to our target distribution for our state space model. So I remind you, for our state space model, our target distribution is this posterior, and we wrote this as this anormalized distribution that I call it gamma, divided by this normalization factor. So we would like a way to come up with Monte Carlo estimates of this using only the anormalized portion of our target distribution. So what I'm going to do literally, I'm going to cut and paste formulas for standard Monte Carlo and importance sampling for standard distributions, and I'm going to apply those to our state space model. All right, so here is the empirical distribution of our target distribution for standard Monte Carlo. So you take n samples, and I denote these samples capital X from 1 to n, because you remember I am looking at target distribution that is has variables x1, x2, all the way to xn. So this will be the I sample of my variables x1 to n. So these are my delta function. So this is my standard empirical measure for the target distribution pi. So if you have any function that is a function of the variables x1, x2, all the way to xn, and you want to compute expectations, the expectation under the empirical measure will be nothing else but the empirical mean, exactly as we have before. So cut and pasting, you substitute in the expectation the true distribution with its empirical measure, and you evaluate the integrals, and this is exactly what you get. And I can write down the estimates for the statistics of the estimator. I can write down a central limit theorem, and I remind you that the expectation under this empirical measure is unbiased. So, okay. And also, I can remind you that the variance is 1 over n times the variance of phi under the true target distribution. Now, somebody can be excited that somehow we have solved our problem, and our dynamical problem gives us basically a rate of convergence that is independent of little n. The problem, however, is that this variance under the target distribution, unfortunately, as we will see, will increase exponentially with time n. So this type of approximation is not going to be useful for a dynamic setting. Okay, so we will need to come up with better Monte Carlo approximations that will make the cost of computing this posterior as we go higher and higher in time, will make the cost to be independent of the little n. Okay, so let's see how we can lead ourselves towards this type of calculations. By the way, let me just, again, cutting and pasting from the previous formulas. If, let's say, you are not interested in the whole joint posterior of all the x's at time n, but you're interested in some posterior marginal, effectively you can integrate all the other variables, and with simple post-processing, you can come up with an empirical measure for the marginal posterior of xk alone by only keeping the delta functions in the variable xk. All right. So we have two difficulties that we need to address in the remaining of the lecture. So, so one of the difficulties, of course, I mentioned, I had a Monte Carlo approximation before for my target distribution. So how do you actually, can you actually compute, can you actually evaluate, can you actually extract samples from this high dimensional distribution as n increases, right? So that's problem one. And then, of course, problem two is, even if you can actually sample from this high dimensional distribution, can you actually keep the complexity, under control? Can you actually make the complexity, at the very best, to actually increase linearly with n? Right. So how do we keep the complexity in n under control? And the answers to both of these problems, of course, will be sequential Monte Carlo. I'm not going to cover sequential Monte Carlo until the next lecture, but let me just tell you what the idea is. We're going to start using importance sampling sequentially, and I'm going to discuss this shortly. But the idea is to build an approximation of the joint distribution of x from 1 to n, given all my y's from 1 to n. I'm going to do it sequentially. And what does that sequentially means? Means I am going to first build at time 1 the distribution p of x1 given y1 and p of y1. And then I am going to reuse whatever Monte Carlo samples were used in this approximation to build the approximation for p of x1 to 2 given y1 to 2, and also of my marginal likelihood p of y1 to 2. And then at time 3, I'm going to reuse whatever Monte Carlo samples I have for this distribution at time 2, and only somehow find a way to sample on my third variable at time 3 and keep going that way in a way that somehow keeps control of the complexity of the problem. So what we're going to do is we're going to do this with sequential importance sampling and using also what we will call later on resampling steps. So for now, let me give you the importance sampling version approximations of the state space model. So remember, our target distribution is this. So we're going to use an importance distribution Q, which is easier to sample from. And this importance distribution, by the way, try not to be confused. This bar here does not indicate posterior, okay? So this is a distribution of the variables x from 1 to n. And here I want to indicate that somehow this importance distribution is a function of the y's of your observation. So you can use information from your observations to compute, to come up with an optimal, if you like, importance sampling distribution. So again, this is not a condition. This to indicate simply in Q. This is to indicate that there is dependency on the observations y's. I remind you that the only assumption I want to make on Q is that the support of Q includes the support of pi, and we said this implies that somehow Q needs to have heavier tails than the target distribution. And I'm going to use the identity that I discussed extensively a few minutes earlier, and that identity is that my target distribution will be written as the product of my anormalized weights times my importance sampling distribution divided by this normalization that you see on the bottom. And as a reminder, what is W? What is little w? Remember, little w is nothing else but the ratio of the anormalized target distribution, which is gamma, or this joint of x and y, divided by q. All right? So you can immediately see from the derivation I have on the slide that, we follow exactly the previous notation. So w again is the anormalized target distribution divided by q, and the rest is exactly as before. So what is the idea of coming up with an importance sampling approximation of my posterior for my state space model is come up with samples from Q. So write down an empirical measure for Q, and from that compute using this equation an empirical measure for P, and that will give you the Monte Carlo importance sampling approximations that we would like to have. So here is my distribution Q. I take n samples. That's my empirical measure for Q, nothing fancy. And I plug in this in the previous equation I had before, right? And immediately what I get is I get an empirical measure for my target distribution. And what is that empirical measure? Is the same delta functions that I had for defining the empirical measure for Q. But now these delta functions are weighted with this capital W. And what is capital W? Capital W are my normalized weights. right? Capital W are my normalized weights, because I remind you here we had the ratio of 2 Monte Carlo approximations, all right? So what are my normalized weights is my little w's evaluated for each of the samples, divided by the sample of all the w's evaluated at all the samples xi, right? Little w, anormalized weight, capital W, normalized weights. So this is the empirical important sampling approximation for my target distribution. And of course, for the non-believers that this approximation does make sense, you can take any function of the states x1 to xn and try to compute expectations under the true target distribution, and you will see the approximation that you get actually corresponds to an approximation of your target distribution with this empirical measure. All right, and how about now the normalizing constant for our target distribution? This is exactly as the calculation we did before. It turns out with direct Monte Carlo that this is nothing else but the empirical, sample, this average of the little w's. These are the anormalized weights. Okay, so effectively the only thing that you do is remember this. This z is the integral of gamma dx. So you can write this as gamma over q times q dx. Gamma over q is w, and you substitute q with its empirical measure, and that's how you get this this approximation. So again, reminder, the anormalized weights is the joint, right, divided by the important sampling distribution, okay? And if you sort of write this, using the product rule, I can write this thing in the this joint distribution as P of y times P of x given y, and this ratio is where the x's come. So you can appreciate that the discrepancy between this posterior of x given y and of my important sampling distribution q is what leads to the approximations that we do with important sampling. And if you want to eliminate those approximations, effectively what you need to do is you need to take this q to be equal to the target distribution. But you remember, this is an objective we didn't want to have to worry about, because sampling directly from the target distribution P of x and y was not computationally feasible, and that's why we introduced important sampling. Still, this identity here is useful because it tells you you like the important sampling distribution to be as close as possible to the target distribution, right? And of course, this makes a lot of sense. All right. And again, you see here the definition of the normalized weights, the little w divided by the summation of all the w's evaluated at all your samples. Now, if you try to compute the statistics of the normalization approximation for z, all right, you remember there we did nothing else but standard Monte Carlo approximation. So the variance of the approximation, z bar of n, if you like, will be 1 over n of the variance of the anormalized weights. And actually, you can, with rather trivial calculation, you can see that the variance of the approximation for z, it is nothing else but 1 over n zn squared times this bracket. And what you have in bracket is really nothing else but the variance of the weights. Okay, so what you have inside the brackets is the variance of the weights. Now, you can bring this variance of the anormalized weights to 0 by selecting Q to be nothing else but your target distribution. This is what I referred to before, and in this case you can see that the variance of the weights becomes 0, and the variance of the normalization approximation for z, it also becomes 0. But again, remember, we don't want to do that, right? This is what we try to avoid. But again, this points to the fact that we need to make the importance sampling distribution as close as possible to the target distribution P of x given y. So here is an equation on if you want to compute approximations, if you want to compute estimates of expectations under this importance sampling approximation. These are again cut and paste the previous equations with a new notation now for our state space model. So if you want to calculate the expectation of some function phi of the states x1 to xn, you substitute the distribution, the target distribution with the empirical measure, and you get your standard result that you see here. And then, of course, by adjusting the notation from the delta method, we can compute the bias of this importance sampling approximation. And again, a reminder that the importance sampling approximation is biased. The bias is 1 over n times this integral. Okay, and I have written the formulas here explicitly so you can see how the I remind you, actually, if you go and you look at the previous formulas, I make a point that here what you had is you had the normalized weights W, right? And that's why the target distribution P of x given y comes directly rather than it's a normalized portion, okay? So anyways, this is 1 over n times this integral is the bias, and the variance is 1 over n times this integral here, exactly the same formulas that we had computed before, and again before these formulas were written in terms of the normalized weights W. Here I have written them for your convenience explicitly. So if you look at the mean square error, that is basically bias squared plus variance, you can see that the bias square is of the order of 1 over n squared, and the variance is of the order of 1 over n. So again, these are standard results that we have visited earlier. So obviously what somebody is interested is to, for these approximations that we saw in the previous slide, we need to find a Q so that somehow the approximation for this importance sampling approximation is optimal in some way, of course, of defining optimality, maybe in terms of variance of this of these approximations. Now, the problem is when we discuss importance sampling, I gave you approximations for the optimal proposal distribution. So you can go back and review those slides on importance sampling. So I gave you the results for the optimal importance sampling distribution, but the only thing I'm going to remind you here is that that optimal distribution turned out to be a function of the test function that you compute the expectation of. So if I have here this function f of x1 to xn, this optimal distribution at time n will be a function of phi of x1 to n, and this is not good, right? Because you would like to have an optimal importance sampling distribution that somehow you can use for multiple functions phi. So this will not work for us, but more importantly, if I try to use this optimal importance distribution, that optimal importance distribution will not be useful in a sequential manner. I mean, having an importance distribution that is optimal at a given time, how is that going to help me to compute the optimal proposal distribution or importance sampling distribution at the next time step? The answer is it will not. And you can think of the following problem. if you look, let's say, at the optimal proposed distribution of time n-1 for this particular function that you compute expectations, then there is almost zero chance that this optimal distribution, importance sampling distribution for estimating this function, that somehow will be even close to the marginal of the optimal importance sampling distribution at time n. And when I refer here marginal, I mean marginal for the variables x1 to xn minus 1, where xn has been integrated out. So if you compute your importance sampling, the optimal importance sampling distribution time n, and you integrate xn out, that distribution that you will get, it will turn out that has nothing to do with the optimal importance sampling distribution at time n minus 1. And you can guess that that will be very problematic for our sequential modeling calculations that were referred to in this lecture. All right, so again, we're going to need to find some approximation for Q that is as close as possible to the target distribution. At least for now, the only thing we can say is we need to keep the weights to be bounded as we anticipate for importance sampling distribution, and we need to be sure that the proposed distribution we choose includes the support space of the target distribution, and this again our target distribution here. All right, so before I stop for the lecture today, let me say a few words about the what's called the effective sample size. All right. Remember that this is our target distribution. This is from where we actually sample. That's the importance sampling distribution, and we will very much like Q to be equal to P. And we said this is not practical. If actually you select Q to be equal to P, then the importance weights are equal. The weights basically will be 1 over n. That's your standard Monte Carlo. The variance is going to be 0. We already have seen this. And if you don't do this, the variance that you get with standard Monte Carlo methods and with importance sampling, they are not the same. And you can show that for functions that they are flat, and I'm not going to prove this, the variance of importance sampling estimate divided by the variance of standard Monte Carlo estimates is 1 plus the variance under the distribution Q of the normalized weights W. Okay? So again, the variance of the importance sampling estimates is 1 plus the variance of capital W under Q times the variance of standard Monte Carlo methods. And that has implications because it can allow us to define what is called an effective sample size. So effectively, if we do, if we do importance sampling, it turns out that the samples that we have are equivalent to standard Monte Carlo samples, but in some with some reduction. And what I mean with some reduction, the number of samples of this. So we take n weighted samples, right, when we do importance sampling, and these weighted samples come from the distribution Q, but based on this relation between the variances using importance sampling and standard Monte Carlo, the number of effective unweighted samples, as if we were doing standard Monte Carlo, it's actually n divided by 1 plus the variance of capital W. And this, of course, is less or equal to n. So how well we do, right, in importance sampling is defined by this effective sample size that you see in the denominator, and that is n divided by 1 plus the variance of capital W under the distribution Q. Now, if this variance is 0, right, then all the weights are the same and the effective sample size is equal to n, and we're going back to standard Monte Carlo. If this variance is very high, then effectively you would need many samples in important sampling to actually make them equivalent to one standard Monte Carlo unweighted sample. There is another another equation to see this effective sample size, and that equation that is more popular in practice is the inverse of the summation of the normalized weight square. All right, so if you want to compute the effective sample size, that it turns out to be 1 over the summation of the squares of the normalized weights, right? This is capital W. Now you can actually show that if you compute an approximation of the variance of the normalized weights, all right? And I leave you this as a simple exercise, so you can actually take the variance of capital W and write this as, you know, integral of W squared times Q minus the integral of WQ squared, and you use all your Monte Carlo approximations for Q. You can actually show that this variance of capital W is n times the summation of the normalized weight squared minus 1. And you remember what I had before for the effective number of samples. The effective number of samples was n divided by 1 plus the variance of W. So n divided by 1 plus the variance of W is actually the sum of this normalized square weights inverse. All right. So this gives you a very nice way to see the effective sample size, and this is what I will use to report in my calculations how well important sampling is doing. Now also you can appreciate this effective sample size from the fact that it's between 1 and n, right? So this makes sense, and you can test this. If let's say all of your weights are 0 except one weight, then that weight, because well, looking at normalized weights, has to be 1. So in that case, your effective sample size is 1. Now, if let's say all your weights are 1 over n, that's your standard Monte Carlo calculations, then you have excellent sampling, and you can, if you put here 1 over n squared times n for the summation, will give you 1 over n inverse, so it gives you n. So that's the case of excellent sampling. All right, so I am going to stop the lecture here, and what we're going to come up in the follow-up lecture will be a discussion of sequential importance sampling. All right, and so we will cover sequential importance sampling, and then from there we will be ready to actually discuss about current sequential Monte Carlo algorithms. Until then, please familiarize yourselves with the notation and the discussion on applying Monte Carlo and importance sampling to the state space model, and we will come back with sequential importance sampling in the follow-up lecture. Bye.